Here we are given a homogeneous equation. And although we are given that it is homogeneous, it's also easy to check that it's homogeneous. So if you just look at the equation, the expression without the derivatives is such that the sum of the exponents, for example, here the sum is just 2. Here you have 1, 1. So again, 1 plus 1 equals 2. And here you just have 2. So the sum of the exponents in all the terms are the same. So here 2, 2, and 2. So you can check that it is a homogeneous equation. Now if you want to do that more formally, the definition of homogeneous is such that, so a homogeneous expression is such that if the expression, the function f(x,y), if and only if it is equal to f, and then you replace the x with kx, you replace the y with ky. So if this is the case, then you know it's homogeneous, because that is the definition of homogeneous. And so let's just try to apply this to our expression. We have our f of xy equals x squared plus 2xy all over y squared. Our f of kx, ky is k squared x squared plus 2 k squared xy. And here we have k squared y squared. And then all the k squareds cancel, and what you're left is x squared plus 2xy all over y squared, which is what we began with, f of xy. And so what we see is that f of xy equals f of kx, ky. And so we know this is homogeneous. And the technique for a homogeneous equation is to actually do the substitution v equals xy, x over y rather. And in this case, this is suitable substitution. So substitute. And so this becomes vy equals x, and therefore what we have will be y dv plus v dy equals dx. And so if we go back to our expression, what we had was dx dy equals x squared plus 2xy all over y squared. Then let's replace that. So the dx bit will be replaced by this expression. So what we have is y dv dy plus v just dy dy, but dy dy is just 1, right? And here what we have, so we have x squared, and we know that this is x, so what we have there is v squared y squared plus we have 2xy, so let's just replace the x with the vy. So what you have will be 2 vy y all over y squared. Let's just simply simplify that a bit. What we get is dv dy plus v equals v squared plus 2v. So the y squareds actually cancel. And we have v here, we have 2v, so what we're left with is y dv dy v squared plus v. And now this is clearly a variable separable equation. You can separate the v's from the y's, and if we do that, we get v squared plus v here. Here we get dy over y. And this integration is not very difficult, right? So let's just begin with the left-hand side. The left-hand side, this bit is dv over v plus 1, and you can use partial fractions. And if this is actually the the denominator, it's quite easy. You do a subtraction, 1 over v plus 1. Here you get a v. So you don't have to, so if you want to go through all the partial fraction expansion, that's fine, but for me this works every time. So you can just check that v plus 1, if you collapse this into one function, you have v plus 1 minus v all over v times v plus 1, right? So if you collapse that, that looks like, and you can just cancel the v's. So you're back with the original equation, and actually you have a dv here, right? And so if we integrate that, what we get is dv equals the integral of this expression, which is not very hard really. What you get is ln v minus ln v plus 1 plus some constant of integration. Let's call it c sub 1. So this is your left hand side, and your right hand side will be this bit. So you get dy over y, and the integration is straightforward. What you get is dy over y equals ln of y plus, let's call it, the constant of integration is called that c2. And now you have left hand side must be equal the right hand side, and therefore ln of v minus ln v plus 1 plus c1 equals ln of y plus c2. Then you can just collapse the constants together, and we can also actually join the logarithms together. What we get is ln of v over v plus 1 times y equals some constant, let's call that c3. And then we recall that our substitution was vy equals x. So this is from our first step here when we learned that this is a homogeneous function. So that step is this substitution, right? So vy equals x. That's our substitution here. And so let's replace the v's there. What we'll get is as follows: x over y all over x over y plus 1 times y. And then let's just simplify that a bit. So you multiply the numerator and the denominator by y, and so you're actually going to get x y plus y squared. So that looks good to me, and this is equal some constant. So you can further do some algebra to remove the logarithm, and let's actually try to do that. So what we'll get is as follows: we'll get something like x over xy plus y squared equals some constant, again c, because e to the c is just, let's say 4 e to the c to the 4, e to the c sub 4 is just some constant again. And so we just raised both sides to, we just raised e to both sides of the equation, right? So e to the ln, e to the c sub 4 here. And this is what you get. You can actually solve for x explicitly or y explicitly, whichever you choose. But here I think this is a good form. So I'll stick with this as the final answer.